In this talk, we introduce three applications from the real world: delay estimation, digital communication, and antenna arrays. Delay estimation is one of the most popular applications that drives not only GNSS radar, but many other applications. The case of GNSS, in which you are on the car, for example, and there are three satellites. They transmit a signal, you receive a signal, and from the delay from transmission to receive, then you can estimate this distance. And if you have the distance between your position and three known positions, you just draw three circles, and the intersection of the three circles is your position. So this is a simplified description and also a simplified modeling, but resemble a real-world case. For a radar, it's very similar, but what changes, here example, you have a bridge and the truck that is passing over the bridge, and while the truck passes, the bridge goes down. This means that the target here in green or the target here in blue reflect the radar waveform, but introduce a delay. And the delay is proportional to the distance between the radar, the target, and back to the radar. And so you do precise positioning in fast time or in slow time. How we can model this case? This case frame into a stochastic process because we can assume that we transmit a signal. We have a linear time invariant system that introduces a delay. It actually introduces a scaling factor. A is a very small number. That means the signal arrives largely attenuated and also delayed. And then, at the receiver, you have addition of random noise that is usually a normal distributed zero mean. And in the end, you have the observation. The observation is the transmitted signal, attenuated, delayed, and added with noise. So it's a process. And the problem are three. First of all, from this signal and from the knowledge of this model, I want to estimate the delay. So what is the best estimate of the delay? How can I solve this in probabilistic terms? The second, when I do this estimate of the delay, how can I tell that this estimate is reliable? I mean, there was a signal or there was not a signal, I just looking any delay in something that is pure noise. And the third question is, how accurate is the estimate of the delay? So in all these three questions, we will see how the statistics and stochastic processes provide an answer. Let's move to the first question. What is the best estimate of the delay? So the problem is framed in this way. We observe the signal, y of t, from 0 to big T, and we have a model of the signal that is a scaled version of the reference signal, also delayed. These two parameters, alpha 0 and tau 0, are to be found. Well, without introducing the complete statistic, I can say that the solution in probabilistic term is that tau 0 and alpha 0 are the parameters that minimize the energy of the error. That means the energy of the distance between the observed signal and its model. So if we elaborate further this equation, we can say that this energy depends on the energy of the observed signal, that does not depend on the parameter, on the energy of the model, that depends a lot on alpha 0, but it's not our interest, and very slightly of tau 0, if tau 0 is a very small delay. And the driver for minimizing the energy is maximizing this term. But this term is a cross-correlation between the observed signal and the model that depend on these two parameters. So here we have the solution. The solution is a value of the parameter tau that makes the cross-correlation between the observed signal and the model as large as possible. And this is, of course, our best statistical solution. But we can say that this solution has an implementation in terms of a matched filter. What is this? We have our received signal, our observable, and we should do the cross-correlation with the reference signal. But the cross-correlation is the convolution with the time-reversed signal. This, in telecommunication, is called the matched filter. Out of the convolution, we have what is actually our cross-correlation, and the position of the maximum of this signal is the delay. In order to understand how it works, let us make two examples. This example changes for the signal-to-noise ratio of the input signal. What is the signal-to-noise ratio? It's the ratio between the power of the signal AX, that is A squared multiplied by the power of X, and the power of noise. On the left, I consider a signal-to-noise ratio of 10, so the signal is 10 times more powerful than the noise. And in fact, we see that the reference signal and the received signal are more or less identical. We can appreciate visually that the observed signal is delayed, and we can also, just by shifting it, compute the delay. But when the signal-to-noise ratio goes to a very low number, in this case, this is a reference signal, but the observed signal is so highly corrupted by noise that I cannot acknowledge that this signal is a copy of this. And finding the delay visually, it was almost impossible. However, if we compute the cross-correlation between the observation and the reference, we see that the cross-correlation has a peak here at tau equals to 10. 10 is in fact exactly the delay that I was assuming in my simulation. In the second case, when I compute the cross-correlation, I see something strange happening. It means that there is still a peak of the cross-correlation that is not really at 10, but very close to 10. But there is also a sort of other spurious peak that eventually, in some cases, they can become the higher peak. So this case in which the strongest peak in the cross-correlation is not due by the signal, but by the noise, is a fact that we have to assess about the reliability of the estimate. And this is what we call the detection. Detection means detecting, so means answering the question, is that the peak we are observing signal or noise? We can model the signal out of the matched filter as two contributions. The red is the contribution of the signal. You see the transmitted signal, delayed, correlated matched filter by the reference. The green is a noise term, that is the noise correlated by the matched filter. So we have a good signal and the noise. And we have a probability that the noise, that in this figure is a green signal, is higher than the autocorrelation of the signal that is a peak. The peak has a power of the square value that is alpha square EX square. And the noise has a power we can compute by this equation, and the signal-to-noise ratio after the matched filter is this value. That is very important in telecommunication, the ratio between the received energy and the noise power spectrum density. But this is a result that for me is important. Output of the matched filter, the signal-to-noise ratio is the signal-to-noise ratio input multiplied by the bandwidth time product. And this is the product of the duration of the observation divided by the decorrelation time, so the number of independent samples. It means that the matched filter increases the signal-to-noise ratio by the number of independent samples that you average. And here, with this formulation, you can compute the result in two cases. What is the result? Is the probability that the green value in some point exceeds the peak of the red. That is basically this tail. And this tail is computed by this expression. The Q function is the tail of the Gaussian. If we put it into equation, we find out that the probability that in any of these positions the noise is larger than the signal is 0.01. But when we compare, for example, this 60 seconds, the probability that there is at least one peak of noise that is above signal is 0.45. So it means that in half of the time, our peak is not due to the signal, but is due to the noise. And so this estimate is very unreliable. And this case is done for the most noisy case. But if we increase just by a factor of 3, for example, the signal-to-noise ratio in the input from 0,1 to 0,3, now the probability drops to 3 parts over 1,000, and this means that we never make an error. The third question is about the estimation accuracy. Also here, the mathematics is not so simple, but let us move to the most important part. This is the received signal, and the received signal, that is the black one, can be decomposed into the true signal, the red one, and the noise, the green one, that summed up give a signal that has its maximum no more in the optimal position, but close to there. And we can compute the optimal delay as a position of the maximum. So the idea is that the position of the maximum is the element that null the derivative of this signal. The derivative of the signal is the derivative of the good signal and the derivative of noise. And so by this relation, we can understand what is the mean value of the error, that is due to the presence of the noise, but as the derivative of noise considering a linear time invariant system is 0, so this means that the delay will be unbiased. The mean values can be sometimes on the left, this can be sometimes on the right, but in the average we are around 0, that is the nominal position. But with the same property, we can compute the variance of the error, and the variance of the error is the variance of this signal divided by this quantity. After some mathematics, we can follow and compute this standard deviation. In our case, we see that the standard deviation for the signal-to-noise ratio 10 is 800 of a pixel, so a very, very small fraction of the pixel. But when the signal-to-noise ratio drops to 0.1, so when the noise is 10 times more than the signal, well, still there is a standard deviation that is 0.8, that is less than 1 pixel.